the issue of the single cycle design in terms of performance of this. So just remembering the single cycle data path, we run one instruction every single cycle sequentially across the entire data path, right? So that means that each instruction just takes one cycle. And this is overall slow because your longest instruction defines your cycle time. So even though your other instructions may be done maybe even halfway through, they still take the same amount of time as your longest instruction. So how can we make it faster? Well, one way is we can run multiple instructions at the same time with pipelining. And in this chapter, we're going to go over what is pipelining, how does it improve over the single cycle, and we're going to do the pipeline data path, pipeline control, and then we have these new things that we need to handle in our pipeline data path, which are hazards and dependencies. Because we're going to have multiple instructions running at the same time. If they are dependent, you have to maybe wait for the first one to finish. Like if we have one instruction writing to register 1, and the instruction right after it is reading from register 1, you better have the correct data from register 1 from the previous instruction before you do the second instruction, right? So you're going to have these hazards. You're also going to have control hazards. What if I have a branch? How do I know which instruction to load next without resolving the branch? And we also cover exceptions and interruptions. All right. So in your reading, they go over this example of laundry. So let's say that the washer is 30 minutes, the dryer is 30 minutes, and it takes around 30 minutes to fold and 30 minutes to put the laundry away. So the way that if we do this analogy for our single cycle design, the way what we're doing in the single cycle design is we're first washing, then we're drying, folding, and putting it away, and then we start the next batch of laundry. Right? So it's like fetching the instruction, reading the registers, maybe accessing memory, and then writing back the results, right? And then we do the next step. But while we're reading, say, the registers, here's the instruction memory is just sitting there doing nothing, right? And this is also not how you do laundry, right? Because you don't just let the washer sit there doing nothing while the dryer is drying. When you're done with the washer, it's available. You're going to start the next batch of laundry. So if you do sequential laundry, like we're doing single cycle, it would take 8 hours for 4 loads. But if you do laundry like how most people do laundry, you can pipeline it. So you start the first load in the washer, and then when it's done, you put it in the dryer, and you put the second load immediately in the washer. So now you have 2 loads of laundry going at the same time, which would be like 2 instructions working at the same time. And then on the next step, when it's done with the dryer, the second load goes into the dryer, and the third load goes into the washer while you start folding the first load. And then here we've reached peak performance of doing laundry, because now every single step is being used. We're putting laundry away, assuming we have 2 people. We're putting laundry away, someone's folding, the washer is being used, the dryer is being used, and the washer is being used. And once we've reached this point, assuming we have an infinite number of loads of laundry to do, we are finishing 1 load of laundry every 30 minutes, right? Because every 30 minutes, the person putting stuff away is finishing that batch of laundry. And a new one is coming in immediately. So we can do something like this in our computer architecture as well. But before we do that, we do have a little bit of time. I just want you guys to talk to each other, think about where else do you see pipelining? This is something that you can see all over. Any examples that you can think of?
So if we had more lows, it would essentially just stand the four.
Yeah.
That's all it would do.
Oh, wait.
Pipelining.
Perfect, is that what you do all the time or what? It's efficient.
Multitask.
Hey, there's something going number two.
Put them together.
Yeah, processing.
Yeah. My buddy, he was teaching me pipelining with the,
Operating system.
Oh.
Oh,
yeah.
Oh, yeah.
That would be a good one.
Yeah.
Might not be really helpful.
Yeah, I'm just thinking.
You could do it somewhere in, right? Because we're like.
Yeah. I was just thinking the most process you're doing.
I was thinking of overcooked, that's why. Overcooked, not like, you know that cooking game where you like do multiple things at once.
No, I don't play
Baker.
A lot of items. Yeah, literally.
Yeah.
Yeah. Yeah.
Yeah, you.
We're not really stumbling.
It's kind of like.
I love my idea of Santa Barbara.
Hey, maybe. No one can think of any good.
Yeah.
No, I'm not.
Yeah.
Do you have it?
No, I heard.
You get your friends?
I got it. I got it.
Oh, really?
Yeah.
All right. So anyone have examples? Pipeline. Yeah.
These guys suggested making like making donuts. Like one guy like makes the dough, and then the other guy fries them, and then the other guy decorates them, and then the other guy sells them.
Yeah. Definitely. Anything else?
We basically said like an assembly line,
Yes.
is that
Mhm.
each person has their own task, so they can keep doing or repeated task over and over, so they get their proficient. Like,
Yeah.
time.
Anything else? Anything?
Burgers.
Anything that's demonstrated. So one of the examples I like to use is roller coasters. The roller coasters, how many roller coasters do you see on the coaster at a time? Like 2, maybe? Yeah, there's more than one. How do they do that? They stagger them. Yes? But how do they, if there is a problem, then how do they stop them? How do they stop the second coaster from running into the first coaster?
Brakes?
They're actually more clever about it than just putting brakes in between.
Oh, really?
What do you need to do on the roller coaster a lot?
Go up with?
Yeah, you need to climb a hill.
Right.
So that's where they break it up. So well, once the first coaster goes to the first hill climb, then the second coaster can go.
Okay.
Because then it'll go down and then you can stop the second coaster because it's at the hill climb. So if you go to the amusement park, you can see these hill climbs and you'll see once the first one clears the hill, then the second one comes and you can watch it.
I thought that was just for like suspense.
Yeah.
That's what I mean, they're clever about it.
Wait, how'd you find out about that?
Just watching it.
Oh, they didn't hit each other.
They do other things too, like at Space Mountain. They do something similar to multi-core. And rather than having one track, they have 2 tracks. They have left and right. They're actually mirrors of each other. So talking about performance, if we have a sequential time for n tasks, then each task is going to take the k amount of stages, so n times k is our total time. But if we have a pipeline for n tasks and these k stages are equally timed, then our performance is just n plus k minus 1 in terms of the time it takes to take. And this is the fill time accounted for. But if we have a sufficiently large amount of tasks, we can ignore this fill time. And then we converge to just taking k amount of time instead. And then we also have to think about what if our pipeline stages are not balanced? This isn't quite going to become a speed up of k. So one thing to note is pipelining does not help the latency of a single task. It helps the throughput of the entire workload. So going back to the roller coasters, they're not making your coaster ride shorter. You still enjoy the whole coaster. But they're able to get more guests on in a given amount of time. And we're able to do this by having multiple tasks operating simultaneously using different resources. And our potential max speedup is the number of pipeline stages, assuming that they're all equally timed. But that is not always the case. So we have to calculate this usually. And our pipeline rate is going to be limited by the slowest pipeline stage. So rather than the slowest instruction, it's the slowest stage. So like if your washer takes 30 minutes, but maybe you live in a very humid environment and your dryer takes 45 minutes, now you're limited by your dryer essentially, because you have to wait for the dryer. So this is going to reduce your speed up that you achieve. And it also takes some time to fill the pipeline and also some time to drain it. So filling it is when we're first starting, like here. We are only using the washer first, but after we reach the beginning of the fourth load, our pipeline is full. So it takes some time to fill it up to reach peak throughput. It also takes some time to empty it at the end of the task. However, for the purposes of your architecture, we're pipelining instructions, and we have billions of instructions in our programs. So this fill and drain is mostly able to be ignored. And we also have to solve for dependencies. So if we have to solve for dependencies, that means that we're wasting a cycle because we're waiting. So for MIPS, we are going to have 5 stages. We're going to have instruction fetch to get the instruction decode to decode the register, the instruction, and read the registers. And then we have execute, which is doing the operation. And then 4 is access to memory if we need it. And then 5 is write back the result to the register file. So given this, we want to look at our instructions, and we're going to assume the time for stages is 100 picoseconds for register read or write, and 200 for all other stages. And this was our single cycle time, right? If we do this, so instruction fetch, register read, ALU operation, memory access, register writes. This is our longest instruction in single cycle. But now we are going to pipeline this and split it up into those 5 stages. So here's our single cycle. Every instruction is 800 picoseconds, right? But now, with pipeline, I first fetch the first instruction, and then when I'm reading the register file and decoding that instruction, I fetch the second instruction. And then while the first instruction is doing the ALU part, I'm decoding the second instruction and reading the register file for that and fetching the third instruction. And by the time I have grabbed 5 instructions, my entire pipeline is filled, and I will finish a instruction every 200 picoseconds. And even though the register file is only 100 picoseconds, our clock cycle is defined by the longest stage. So this is where our performance is being impacted. So we want our stages to be as equal as possible to reach our max throughput. We also want to have as many stages as we can. So just so you know, we're doing a simplified design. We have 5 stages. CPUs nowadays, any guess how many stages there are? It's just a guess, like.
It's, you asked how many stages there are?
Yeah,
5?
like on actual CPU designs from Intel or AMD nowadays. What do you think?
Million.
1?
No, that would be single cycle.
It's more.
Yes, it's definitely more.
Couple thousand? 15 or 32?
You're the closest. Yeah, so it's around 20 to 30 stages. So we can't just teach you that, right? It would be impossible for you to understand that. So we start with simple 5 stages. But just for your reference, they're around 20 to 30. So that means at any given time, when you're running your CPU, there's 20 to 30 instructions being executed at the same time per core. So this is your full everywhere question. Which of the following is true about a pipeline processor? So do this individually first. Let me tell you your code. It is 692. Six nine two. All right, I don't see any new answers coming in. You guys are well past the threshold. So anyone want to tell me what this? Yeah.
So, like in the case of laundry, per se, each person's task still takes the same amount of time. You're just kind of moving it so they can do it more efficiently. So I feel like the latency remains unchanged, but your throughput is much more.
Yeah. Your throughput is it's increased by the number of stages. So what about these overheads? What are these overheads?
like the fill and the drain and, possibly like stalls if you need it.
Yeah, fill, drain, stall, and then one other thing is, what if your stages are not perfectly equal? Right? So the instruction latency of this, of an instruction is actually 1,000 seconds, right? Whereas single cycle, it was 800. Because we have to clock our CPU by the longest stage. So even though reg is only 100, it takes 200. So those are some other overheads. But overall, we are going to increase our throughput. The maximum theoretical increase is by the number of stages, but we don't usually reach that. Right. So how can we split up our data path in order to support pipelining? So we're going to divide it into these 5 different stages, right? This is instruction fetch. Okay. This is instruction decode and register read. This is execute. This is memory access, and then writing back to the register file. So what sequential component should I put in between these different stages in order to save the results of the instruction fetch and then start the instruction decode and be able to start a new instruction fetch? What component saves things? Registers. Registers. Yep. So we are going to add pipeline registers to our data path. So the registers are going to hold information produced in the previous cycle and to be consumed in the next clock cycle. So what happens is you get your instruction fetch. The first instruction will be an instruction fetch. Then this pipeline register will keep PC plus 4, as well as the 32-bit instruction. Next clock cycle, PC plus 4 was saved into the PC register. So the second instruction can be fetched. And this pipeline register holds PC plus 4, as well as the instruction. So now it can read the registers while this is fetching the next instruction. And then the same thing for the other registers. So we're going to go through some examples of this. So we're going to do the pipeline diagram, which is going to show the pipeline usage in every single cycle. And it's also going to highlight which resources are being used. There's also the multi-clock cycle diagram. But we are not going to cover the multi-clock cycle diagram. This is the chapter in the book that I have you guys skip. So let's look at the single clock cycle for load and store. So let's say we first fetch a load word. So we increment PC by 4, store that into the PC register, and get the memory out of the instruction memory, and store both PC plus 4 here and the load word instruction. Next clock cycle, we just follow the load word. It's going to get PC plus 4, and it's going to save that into the next pipeline register. And it's going to decode the instruction and read the registers. So it's going to get the base address and the sign extended immediate over here. And one other thing that is stored in this pipeline register is going to be the RT. What is RT? Where am I storing this? The next clock cycle, we're going to do our execute. So we're going to get the sign extended immediate and the base address, add them. And then this is going to be PC plus 4. And next clock cycle, we have our calculated address. And we're going to get the data out of the data memory. And finally, I told you that this is going to also propagate RT. So we get the read data as our write data, and RT is our write register. And that is our fifth cycle. So there is a problem with this. So what is the problem? I mentioned it already.
Be like a overlapper. It's like right at the right back, you're putting data in the register, but then like at the, like,
It's possible, but with our specific instruction sets, when you're at this stage, you're only reading, right? You're never writing at this stage. How do I know which write register to write to?
We're missing a mux, right?
Where? Oh, it doesn't show.
Oh.
So that is one thing, but the other thing is we don't show how we're propagating RT here. Like you need to be able to propagate RT throughout here so that we remember this instruction was supposed to write to RT. Like, and RT was, say, register 8. But we don't have anywhere showing it propagated through. Okay. So if we don't do that, then I'm just going to write to the register that this instruction is trying to do. So this is our correction. We get the writes register, and now it's propagating through our pipeline. And it comes back around. We also need to do the same for our control signals. Our control signals are going to be generated here, and they will propagate through with the instruction. So now, let's do store word. So store word, fetch, decode, and now we execute. So execute is the same as load word, right? Your base address plus the sign extended immediate. In memory, I'm going to write the data from RT to the address I calculated. And what about write back? What do I need to do in write back?
Need to write from memory to register.
I'm store word.
Oh. So you don't need to do anything.
Yeah, I just don't do anything. Right? So that's kind of just the introduction to pipelining. So pipelining is going to improve performance by increasing our instruction throughputs. And we increase our instruction throughputs by executing multiple instructions in parallel. And each instruction has the same latency, minus some overheads that we talked about. And we'll go over this in more detail, but they are subject to hazards that prevent starting the next instruction in the next cycle. Like if you have a branch, how do you decide what instruction to do after the branch? It's either going to be taken or not taken. We have to handle that. And we do this by splitting up our data path into those 5 stages and putting those pipeline registers in between each. And all data belonging to one instruction will be kept within the stage that that instruction is in. And everything that happened in any previous stage will be overwritten because the next instruction is coming in. So we will go over more details what this single cycle pipeline diagram is, where we're going to show a table basically that describes what is being used in each stage. And it's very similar. Show you. It looks something like this. This is your cycle by cycle. Like this is first cycle, second cycle, and this is the usage, right? So that'll be our pipeline diagram. But that is our introduction to pipelining. Your test will not include pipelining. So what we finished in our slides at the beginning of lecture, that is what exam 2 will be up to, which is homework 2 and homework 3. And homework 3 is release. It is due Monday when you come back from spring break. Exam 2 study guide is also released. You will read, actually, this will be much later because when we come back, Monday will be review of arithmetic, and Wednesday will be review of single cycle, and Friday will be exam 2. All right, so just a reminder, do not come to class on Friday. This Friday, class is canceled.
Yes.